Hello, everyone, and welcome to the 32nd Surface Ventures keynote webinar. So great to see you all here loaded in. Could I just ask that you say hi in the chat box and tell us where you're joining from today? My name is Dr. Sam McMaster. I am the event manager at Surface Ventures, and we are a not-for-profit organization, and our mission is to provide world-class material science education for academia and industry. Today, it is my pleasure to introduce Dr. Peter Lee, Institute Engineer and STLE Fellow from Southwest Research Institute. So after working as a qualified automotive vehicle mechanic for a number of years after leaving school, Peter attended the University of Leeds, where he attended a first bachelor's degree in automotive engineering, and then a PhD in engine tribology. Peter continued his work at the University of Leeds for a further 5 years as a Royal Academy of Engineering Research Fellow before moving to SwRI to establish the tribology labs. Many thanks to today's partner, Total Seal Piston Rings. We'll be releasing links to their YouTube channel, and Lake Speed Jr. from Total Seal will be joining us for the Q&A session. As we go along, please type your questions into the chat, and they'll be marked for the Q&A sessions later in the event after the presentations. We're planning to go for around 60 minutes in total today, and we will be sharing a link for the attendance certificates later in the event. So without further ado, let's welcome our speaker to the stage and then proceed with the webinar.
Well,
hello, welcome, Peter. Let me just bring your slides up.
Perfect.
There we go.
Okay, well, thank you for the introduction, and thank you to everybody for joining us. Before I dive into the development of this variable hardness coating that we've done, I'd like to take a few minutes to introduce everybody to Southwest, just because it's the unique environment at Southwest that has enabled us to be able to do this coating. So this is a aerial shot of Southwest campus in 2011 when I started here. It's about 1,500 acres in northwest San Antonio. It used to be a long way out the city in 1947 when it was established, but clearly it's not now. It's somewhat surrounded, so it's quite a pleasant little oasis within a very built-up area. We have 2,700 employees, about 2.5 million square feet of laboratory space, and the research volume reached about nearly 800 million last year. We're involved in every market segment. This makes being in the tribology group, and one of the main reasons why I came here, really, really interesting. You know, we never know what's going to come through the door, what we're going to be doing next, and that's really makes it really exciting environment to work in. Being one of the world's largest independent providers of advanced scientific and applied technology solutions, we basically do contract R&D problem solvers, and that's mainly what we do. 1,500 of our staff have degrees from about 500 universities worldwide, and we have a very good representation of staff from all around the world, and we sponsor those on their visas and bring them in, which is obviously how I ended up here. I would say that diverse research is the DNA of where we are. We've got departments in 11 technical divisions that cover the complete spectrum of engineering and physical sciences, from really deep sea to deep space and everything in between, which sounds like a bit of a grandiose statement, and it kind of is, but it's genuine and it's true. If you go to our website, you'll be able to see that. As a non-profit research and development organization, we actually use part of our revenue to invest in tomorrow's innovations. So we don't have to pay shareholders, so we're able to reinvest all that money profit that we make into the facilities, the campus, and research. Last year we did 89 new projects, and that was an investment of $7 million in internal research. The IR&D fulfills the Institute's objective of conducting innovative activities for the benefit of industry, government, and humankind. And by investing that internal research, we're investing in the technology that our clients might need in the future. The program also allows our engineers and scientists the freedom to explore innovative and unproven concepts for the benefit of not just the clients, but also it means that we as staff can do that without the contractual restrictions and expectations. So it's much more free, and you're able to really come up with ideas and start developing things. And that is where we fit in the technology spectrum, really between the universities and national labs that are doing the fundamental science and the industry, where they're bringing this to reality, as you might say. We do some fundamental science, mainly through the IR program, but we then bring that through to reach a point where we do very small scale production, but not big scale, just enough to prove the concept, and then that goes out into industry, and industry will take that. So what I'm presenting today has been achieved through a series of 4 of those internal research awards. And there's obviously not just me, there's been a very large group of people. I haven't acknowledged them all on here, but it's gone across a lot of sectors. It's gone across engine and driveline sections, engine development. It came out of the coatings lab, where we have specialists on coatings, and it came through my tribology lab, where we looked at some of this stuff, and then we'll see where it goes from there, really. So the very first IR&D that we undertook was actually over a decade ago, and it was the development of a new coating process. It's based upon physical vapor deposition. Obviously, PVD describes a variety of physical deposition methods that can be used to produce thin films on substrates, including glass, ceramics, metals, and polymers. Material transitions from a condensed phase, whether that be liquid or solid, to a vapor phase, where it's transported to the surface of what you're trying to coat, where it then turns back into a solid condensed phase as a thin film. The most common process for conversion to the vapor phase is sputtering or evaporation. Magnetron sputtering utilizes a magnetic field and an electric field to confine particles near the surface of the target. That increases the ion density and results in a high rate of sputtering. Magnetron sputtering is an exceptionally versatile method for thin film deposition. Other deposition methods are limited to the materials they can use as the sputtering target. So the source material can be almost anything with magnetron sputtering, since it doesn't need to melt or evaporate the material. The sputtering deposited film, will have a composition that closely matches the source, and it will adhere to the substrate better than evaporated films. Some of the major advantages of the process are a high deposition rate, thorough coverage of materials, a high purity of the films, highly adhesive films, and a uniformity on large areas. And with regard to piston rings in particular, the low temperature is very beneficial. In the plasma-enhanced magnetron sputtering process, which we developed at Southwest, while the atoms are sputtered from the magnetron targets, ions from the global plasma can be bombarded in the surface of the substrate, including the sputtered atoms of titanium. And these produce a protective coating, including the atoms from the gas, on the surfaces of the negatively biased substrate. So the discharge conditions caused by the condition of the global plasma is effective in inducing the reactive gas to react with the metal atoms. This then forms the tin, silicon, carbon, nitride coating. And this process is capable of laying down films of up to 40 microns thick. Obviously, we don't need that thickness for piston rings, but we have used that for other purposes. Now, the second IR&D was undertaken in 2013, and that was in response to the increased need to reduce friction in vehicles to improve fuel economy in order to meet the corporate average fuel economy targets. You can see on the graph they were becoming very strict at that time and projected in the future to become even more strict. And so it reached a point where almost all the low-hanging fruits had been got from the car manufacturers, and we were needing something that was going to really make a difference. And so we targeted piston rings. So by targeting the piston rings, what we did was a thick coat of CRN. Sorry, I apologize. No, we didn't do a thick coat of CRN. What we're looking at here is the limitations in 2013. Obviously, some of this has developed since then, but in 2013, there were limitations for traditional piston ring coatings. They used CRN coatings of up to about 50 microns in diesel engines. That's okay. In diesel engines, gasoline's not so good, but it has a high dry coefficient of friction, and so that's obviously not great for fuel economy. DLC coatings weren't really commercially accepted in about 2013, and there was really insufficient coating thicknesses at that time. And the tin, silicon, carbon, nitrogen, and nanocomposite coatings that we developed had some of the advantages that they were super hard, they were thick coatings, erosion and wear protective, but they did still have high coefficient of friction. Now, what we did is we developed the coatings further, and we did some more work on this, and we started to look at how we could do that. And what it is a nanocomposite coating that consists of, didn't plan this out very well, it's hiding my screen, nanocrystals that are embedded in the silicon carbon nitride based amorphous phase. And we patented that, and we also patented the particular ring coating that we were looking at doing. And now the way to think about this is actually, if you look at that image of the surface coating up there, if you change that and you think about that as cookies, basically. So chocolate chip cookies is a perfect example of how those coatings are looking. What we did is we took this and we tried probably about 12 different types of coatings. So this method is kind of tunable dependent upon the amount of gases you put in and how you use it. And we tried, like I say, about 12 different coatings. We put these into the reciprocating T77 rig that we have here in the tribology labs. Now, what we do there is we take a real piston ring after it's been coated and real liners, and we cut those up into the sample parts that you see on the right-hand side image there and the left, the big image. And we put oil in there and we reciprocate under different loads and different frequencies. And what we do is we measure the friction coefficient. And what we did is we had our original coating, which we're calling base 4 on this graph. And I haven't put all 12 on there because you can't differentiate between the lines if I do that, but I've just put some example ones on. So some of them you can see they increased in friction and some of them decreased in friction. And the CIR11 coating that we developed actually gave us a 10% reduction in friction at that 20 hertz position. And so that's the one that we then took and we worked further with that one. But to check that it was really giving us that answer, we coated some piston rings for our Ricardo Hydra engine, and we put them in there and we ran them in that engine. Now, you can't really see the engine in that left diagram because it's surrounded by all the ancillaries. But basically, if you look in the middle there, we have sensors on the side there which allow us to be able to measure the friction response. And they're in the Wheatstone bridge configuration so that it doesn't account for bending, it equals that out. And what we did is we therefore measured directly the friction on the connecting rod of the piston assembly. And from there, we can, knowing the forces and the pressures and everything else, we can calculate what the actual friction is. And it gives us graphs that look like this. So on the left-hand side there, you can see we've got the full rotation of the engine through intake, compression, power, and exhaust. And it allows us to actually study in detail and see where throughout the engine process are we reducing the friction the most and having a good impact. On the right-hand side, you can see we built the engine and we ran it with the standard rings. We then put in the coated rings we'd developed, and then we ran again with the standard rings, and on average we saw a 39% reduction in coefficient of friction. Obviously you're not going to see that in an engine. No, it's a little bit biased in the single cylinder Hydra engine because you haven't got as much stuff as you have on the full size engine, but it still points in the right direction of the effect that we have. Now that's okay if you get low friction, but we're also needing to know that this is going to last. So we also took this and we did some durability tests with a 2.4 litre Caterpillar engine. This is a standard ASTM engine test. We modified it to accelerate wear of the piston rings and cylinder liner. So baseline and coated rings were running it. We do weight loss of the piston rings and dimensional change in the cylinder liner. I haven't gone into details here. It's not really the focus of this presentation, but we ran it with a 4.1% SUP. And therefore, obviously, if it's running with pre-sutted lubricant, that's higher wear oil than you'd experience if it was brand new. Did 252 hours and 350 kilopascals, but that basically high pressure and relatively high engine temperature. The summary of that IR, when it came to an end, basically said that we'd showed a 10% reduction in COF in the reciprocating rig, a 39% reduction on average in the gasoline engine. We had a reduction of 28%, 48% in weight loss for the coated top and second rings in the diesel engine, and a 50% reduction in liner wear, which obviously shows that we've managed to develop very successfully some sort of piston ring coating. But vehicle manufacturers are not going to buy a piston ring coating from you based upon that. They're going to license that piston ring coating based upon actual behavior in a vehicle, a full vehicle. Now, as you can see on this graph, this is what the situation was. We had precision versus relevance. Now, obviously, the full vehicle is very relevant. That's what the manufacturers want. It's very difficult for them to understand what you're doing on the bench rig. But the bench rig is where you have your precision. And so what we needed to do was develop a system where the vehicle could be as accurate as the bench rig. And that is why we need to do this. In the past, it's been easy. You know, if you have a fuel economy change from 20 miles per gallon to 27 miles per gallon, that's really easy to do. But if you have a fuel economy that's going from 20 to 20.5 or 21 miles per gallon, that's much more difficult to show and actually have a significant change that's outside of the noise of the measurement system. So we needed to be there. And so what happened was we asked for another internal research project. Now that internal research project basically took the method that's used for doing fuel economy, which is a combination of a federal test procedure, which is representative of city driving, and the highway fuel economy test, which is representative of just being on the highway, as it says, and run both of those tests and combine them to give you a typical kind of fuel economy improvement. But when we run those tests, not currently, but back then when we applied for this IR, when we ran those tests, what happens is you have a person sat in a car on a mileage dynamometer, and they're using the accelerator pedal to accelerate and deaccelerate and follow what they're supposed to be following. Well, you know, accelerating and deaccelerating can be very, very small movements. And every time you do that, you're changing the fuel economy. And so that's where the error comes in, because a human being trying to repeat the same thing time and time again is not going to get it exactly the same, never mind how good they are. So what we did is we developed a system in the IR where we were able to measure the input signals. So the advantage of going from a cable powered accelerator to a electronic input allows you to measure that electronic input and then feed that back into the vehicle instead of the human being doing it. And that meant that we were able to repeat and get very, very fine accuracy. And so we were then able to take this, again, another IR, where we wanted to demonstrate the fuel economy improvements of this coating we developed in a full-size vehicle. Now, what we did is we took happened to have that Hyundai lying around, not being used after it had been used for some other testing. So we took that vehicle, we bought a new engine and ran it in, and then we installed a modified ECU so we could conduct the testing we wanted to test, where we can input the signal and get the repeatability. We then installed Part A, which are the original OEM ring set, and we ran them. Then we tore the engine down and rebuilt it and ran with Part A again, the original OEM parts. The purpose of that was to look at the effect of tear down and rebuild and make sure we weren't affecting things negatively by doing that. We then checked for a fuel economy shift due to that and found that there wasn't one. So we were able to rebuild without problem. So then we installed part B, which were the OEM coated piston rings with our coating on them. And then back to the original OEM parts, and then back to our coated rings. And what that gave us was the results that we see here. So we take the fuel economy test results and the highway test results, and we combine those, and we were finding a 0.3 miles per gallon improvement if we look at the average over those results. So in summary, we managed to show that we could actually, in an entire vehicle, save some fuel economy. So why variable hardness? Why have we now moved from that piston ring into a variable hardness coating for rings? Well, Total Seal and Southwest are working together to further understand the effect of the run-in of cylinder liners. So if you want to have a well-sealed liner, you need to make sure that you've got basically as little gap as possible between the ring and the liner. And to achieve that, you need the parts to run in very effectively and very smoothly. You don't want any scoring on the ring. You don't want any scoring on the liner, which basically creates small gaps that gas can get through. You want your blow by to be as low as possible so that you're managing to use all that power for fuel economy. And so we're looking at that, and we're looking at how different coatings, different liner finishes are going to match together, and what's going to give us the best run-in and the best ultimate thing at the end. Now, what we did observe was that softer coating gives a better run-in, but that isn't any good, because that coating is eventually just going to disappear because it's soft. And then what you need under that is a hard coating. So if you do that, and here's a picture of a piston ring, if you do that, you're at this point saying you need a dual coating. Now, dual coatings unfortunately don't work that well. You know, one of the things that Lake tried while he was working in the labs with us was a WCC on a CRN, and it delaminated. You can see on the top edge there where it's beginning to delaminate, and a few spots on the main ring where it's touching. That delamination is not good. That delamination is working against exactly what you're trying to achieve, because you then have small particles in the oil that are going to basically get between the ring and the liner and create those scores that are exactly what you're trying to not have and get rid of. So we came up with the theory. If using a softer coating for running gives a softer run-in, so less damage is done to the surface of the liner by the asperities as they're removed, and a single layer variable hardness coating might be possible. It would solve the shortcomings of the single layer, single hardness coatings, and it would remove the delamination issues of the dual layer coating. Now, we'd already previously patented our friction nanocomposite coatings, and we went down to the materials lab and coatings lab and spoke with the technicians and engineers down there and said, you know, we already know that we can take this coating and we can make it different, because we did that 12 times in the previous IR. Well, what if you can change the deposition of the coating during the coating process? So basically dial it in from a hard coating over to a soft coating right at the end and see whether that has an effect that we're looking for. Well, the plan was to apply various running coatings on test rigs and see if that works. So that's what we did. We did, again, a series of, I think this time about 6 different coatings. Or we tested the coatings in the reciprocating rig to try and find improved running characteristics. We selected the best one and applied that to a full set of rings. I then packaged those rings up and sent them to Lake Speed, and he put them in the NASCAR engine, first with baseline rings, which was CRN, and then with our variable hardness rings that we sent him to find out if it was genuinely having the effect that we thought we were going to be seeing. This was very much a team approach. We pretty much finished everything that's in the red box there. We applied the coatings, tested them in the T77, and had my travel covered for the project. Total Seal Piston Rings supplied the steel rings that we were coating and playing with, and then covered Lake Speed's travel to go and do the NASCAR engine test. Rottler Manufacturing supplied us with a test liner and honed the liners for the engine test. So they were honed exactly the same, and they were the same liners, so we're able to cut those up and then run them in the T77. And the ProMotor engines built the engine with Lake and provided the dyno testing capabilities to try this out. And ultimately, the plans to go to Tony Stewart Racing and trial these rings in a car on a track and actually see if they're having the desired effect. So let's start the beginning of this with the T77 testing. As I said, it's the same liner for all the tests. We used the 5W30 oils, the same one for all the tests. We ran 2 tests with each ring just to make sure we weren't seeing any outliers. Baseline TISICN ring that we developed previously, we coated, and that we used that as our baseline. And then we tried 4 different variable coating rings. We did 6, but 2 were clearly not working, so we only had 4 that we could try. Same test sample profile developed for Lake's running investigations. So 20 Hertz, 20mm stroke. We start off at 100 newtons and then put that up to 400 newtons. We measure the friction throughout the test, and we have images at EOT and measurement of the wear at the EOT as well. So here are the results. You can see that the purple is the baseline, and we have VH5, 6, and 7, and 9, which are the 4 coatings that we tried. You can see that we have the 2, which are actually higher friction than the baseline, so that's an undesirable outcome in this situation. But they're also quite noisy, and you can see we have 2 coatings that have run in nicely and are lower friction and actually much less friction noise in there as well, which is highly beneficial and what we're looking for. So we're now just going to look at VH6 and 7 moving forward, because we've already discounted 5 and 9. What we're going to look at is the liner specimens. So note, you can see, if you look closely, you can see the crosshatch on the test surface there. These are just the fixing holes that we screw down to the base of the T77 to hold it in place while we're doing the testing. This is the reciprocating ring contact. So the ring is reciprocating backwards and forwards on that area. And this is the wear scar area that we're going to be looking at. So that's what you want to be focusing on the next few slides. So this is the baseline. You can see, looking at the baseline, you can see some of that scoring that I was talking about, where there's lines along the line of reciprocation. And you can see on the ring, there's a little bit of wear on the ring there, just on one edge, which is normal behavior. VH6 wear scar, you look at that one, you little bit more hard push to see exactly where that wear scar area is. And the ring's looking very similar to the last one, so no poor effects. If we look at VHX7, you can see that's not coping quite so well. You can see a lot more wear from it on the ring, and you can also see those lines and wear on the liner that we're not really wanting to see. So VH6 is a clear winner. All 3 there just for comparison, so you can look at those together. There's more ring wear for VH7, similar ring wear for VH6 and the baseline. You can see the distinct ends of stroke on some of them, but not on the others. White light data I've not presented, that can be a bit confusing, but that confirms the same as the visual that we're seeing here. So VH6 is a clear winner. It's the lowest friction and the lowest wear. So let's take that and coat it. So here we have a stack of rings which are inside our coating chamber that are being coated with the VH6 coating. Here you have a fuzzy lake in the background holding up a piston with those installed. So that was the first and the second ring that we coated. This was put into a Ford C3 NASCAR engine with Yates head engine. This is a 358 cubic inch V8 engine. It was actually the one that was raced by Lake Speed. So that was a nice little touch there, that we're using that to try and develop stuff. And this is the engine on the dyno where it did the runs. So this is the torque that we get from the chrome ring, the original ring that's in the engine. So we do the dyno runs and we measure the torque. And then this is what we got with the VH6 ring. So you can see quite a distinct improvement there. We have a 1.3% increase in peak torque between the chrome ring and the VH6 ring there. A slight change in speed, but not much, from 7,200 down to 7,100, but that's good. And oil temperature and water temperatures registered there, because obviously that's important, because we'd want to know that this is due to the ring and not due to a change in viscosity of the lubricant because of a change in temperature. And then here we have the horsepower results. So there's a plus 0.6% increase in horsepower. Again, very similar speeds. So we're seeing that we're having a positive effect on horsepower, which is effectively fuel economy. And wear as well. So we did ICP results. I've taken off the chrome, the iron, and those readings, and just put in what the components that they're coming from. So you can see the valve train cylinder bore wear is down considerably with the VH6 ring. So that's advantageous. Now, obviously, the bushing and bearing wears down because you haven't got as many particles floating around in the oil that have worn off from the valve train or the cylinder bore or the rings or anywhere else. So that reduces wear overall in your engine. Here's a combination of the CRN and the VH6 rings at the end of the test. So you can see that they're working very similarly. You can see that the CRN is quite hard because there's hardly any wear. And you can see on the right-hand side with the VH6 ring, you can see that center line of the top ring where it's been rubbing on the liner, and you can see that's slightly more wear because it's worn off that soft layer and got down to the harder layer. This is the second ring. Again, very similar results. You can see the left-hand side, very little wear, right-hand side a bit more wear. This is not like a top ring, it's shaped differently, so the majority of the wear is down the bottom. That's where you need to be looking at this. Interesting was the blow-by and run-in. So blow-by is an indication of how well those rings are sealing, like I explained at the beginning. You want to reduce blow-by. The CRN coating was down at 2 CFM after 30 minutes of running, whereas the V6 coating effectively ran in almost immediately and was down at 2 CFM, basically as soon as the engine started and they were taking the measurements. From a running perspective, the V6 coating remains the same at 2 CFM through all 10 power runs. And this indicated that the running was almost instantaneous because that blow-by did not change throughout the testing. What we still need to do to prove this out a little more is to run a prolonged time in a race engine, just to make sure that we've got the durability there that we're wanting to have, and that we don't see any tick up in wear due to anything happening. We also would like to run the baseline rings in the NASCAR engine as well, just to get a baseline there of the TISICN ring that this technology came out of, which would really show how the dual coating, well, it's not dual coating, how the variable coating is actually changing the run-in and has an advantage effect. So to summarize, the variable hardness coating actually exceeded expectations, demonstrated significant efficiency gain compared to the baseline chrome coating. We saw increased torque, which is equivalent to acceleration of about 1.3%, increased horsepower, which is fuel economy of about 0.63%. On top of that, the ICP results suggested reduced wear, which is highly advantageous, and run-in was almost instantaneous, which is also doesn't matter so much for everyday vehicles, but for race vehicles competition vehicles is very, very beneficial. So thank you very much. Hope that was interesting, and I'm open to any questions.
All right, thank you very much, Peter. That was a fantastic presentation. Okay. Okay, so now I think what we like to do is let's invite Blake on stage as well, and we can begin to take questions in a moment. We have a few in the chat already, but before we sort of do that, let me just release a video link there as a featured action. So if anyone is interested about the history of piston rings, please do click down in the bottom left. And there are also 2 more YouTube video links in the chat from Total Seal Piston Rings YouTube channel. Okay, so let's begin with our first question from Shuberjit, who asks about slide 10. He says, the surface looked wavy. Did it affect the engine performance? Should we scroll back to...
Better eventually. Okay. Oh, that's really, that's 5 nanometers that you're looking at there. No, it didn't. It didn't affect the engine performance at all. And so these things are embedded in there, but it's not. How can I explain? It's so small on the 5 nanometer scale that particles don't affect or create a problem.
Of course. Was there a roughness measurement made before and after coating?
Yes, it was. I didn't put that in.
Okay.
But it was slightly smoother afterwards, but not by much.
Mm-hmm. Mm-hmm.
And we had to use white light interferometry to get those measurements because of the small scale.
Of course. Okay, so let's move on to second question. I think Lake will be back with us in a moment. He just has a slight audio issue, so I'm sure we'll be back in a second. But I think we can proceed with this question from Mark, who asks, I may have missed it, but what is the material / coating of the cylinder liner for the ring coating comparisons?
I think you're best answering that one, Lake, since the liners came from you. Well, Bottler.
Right, yeah, so the bench test, the TE77 test, those were ductile iron liners, the aftermarket ones we purchased. Mm-hmm. And then the race block itself is also, I'm not exactly sure of the exact metallurgy that Ford utilized. That is not compacted graphite, but it is what they call their higher nickel cast irons.
Okay, thank you. Just to let everyone know who is awaiting the attendance certificate link, I'll share that now. So if you like an attendance certificate, please do click on that, but don't leave the webinar. We will be continuing with questions. And if you want the link, please do click on it now, as it won't be available after this event. Okay.
Also, just for reference, the base ring material was stainless steel, so 440B stainless steel is what we use in all those tests. Non-nitrided, just coated.
Got it. Thanks, Lake. Okay, so next question here from William, who asks, are these liner samples oriented as we might see them? As in, up is deck side, down is crank side, looking at the Hone crosshatch angle. So I think that was... We're looking at
that'll be on the T77 sections on the slide. So when you're working on the T77, you have to be a little bit more aware of how it's operating. So basically, you can't change the load. So you have a fixed load, and it's reciprocating backwards and forwards. The way that this is orientated is that the top and the bottom of the liner are to the left and the right hand side of the picture. And so the curvature is from the top to the bottom. And the rings therefore matching the curvature of that liner sample and reciprocating from left to right, as if it was going up and down. But you really have 2 kind of top dead centers where it stops, because you can only load it to one load. You can't replicate the load at the top dead center on one point and the bottom dead center at the other point. So if you're doing a 20 millimeter stroke, as we were here, you've got the first 10 millimeters from top dead center down, and then it's doing the same again as it comes to a stop again, as if it's a top dead center. So it's a little bit different to real engine testing, but it replicates the more severe condition of top dead center.
Mm-hmm.
So I think one of his questions was looking at the crosshatch angle. So those are honed at a 45-degree crosshatch angle. So we honed all of these on a Rottler CNC hone. H85AX is the hone we use to do that. Actually, Ed Keebler from Rottler is the guy that actually honed all these liner sections. We built a little fixture so we could hone the sleeves and do all that. And we checked it. We have a optical crosshatch angle checking tool. So all the cylinders we ran all had the same crosshatch angle, all 45 degrees. And to change your orientation, just rotate that counterclockwise 90 degrees, and then that would be how it runs in the engine.
Okay. Thanks, Blake. So let's proceed on to the next question from Hamid, who asks, what are the substrate materials that you could have this composite coating on?
In theory, pretty much anything, because of the way it's produced, as long as it would adhere to it. It's the type of coating it is. It can go on, you could have it on glass, ceramics, some plastics, I suspect, if they got high enough temperatures, because it's a low temperature process, a relatively low temperature process. So, yeah.
Okay. Thank you. So I have a question from Jill here, who asks, would these coated piston rings be compatible with an anodized piston?
Absolutely. With the engine we ran, did have anodized ring grooves. So sorry, Peter. But yes.
There we go. We like easy ones like that sometimes.
That was too simple. One thing, I know we only have so much time, but when we were, as Peter was mentioning, the way it strokes, one thing about this, when we looked at the optical profilometer results on this, and you took a track and you measured the entire length of the test surface. So you could go from the unrun through the run back to the unrun. You can literally see the stride bet curve taking place. You can see where it valleys out, where you're in boundary condition. You can see the mixed film. You can see the full film hydrodynamic in the middle. It was incredible. The first runs we ran on this were like, wow, you can like literally see it. It's so neat. I can't help it. I geek out about it every time I see it. I've got it saved on a screensaver of mine. It's so cool. So anyway, sorry about that.
No, I mean, that sounds fascinating. It's one of those things that seems like, it's really rare for you to actually see that in in anything that's not, any kind of lab scale test. So, yeah.
So when we were working on trying to work out, okay, what should this test sequence look like? And we were trying to hone it in, and we spent a lot of time working out, working the maths of, okay, we know we do this on engine testing, and this is what it looks like. These are the speeds, these are the loads. Let's try to calculate it over and get in the ballpark. And we came up with this idea, and we ran it, and we were like, okay, let's run it back and throw it in the Bruker and take a look at it. And it popped up, and we were like, yep, we got it. First time. It's better be lucky than good.
Okay, so let's move on to another question here. It's a little different, it looks like, from Dell, who asks, when diamondoids are added to motor oil, they initially show reduced friction, but after many hours of operation, the diamondoid additive begins to increase wear. Have you conducted testing for extended periods of time, over 1,000 hours?
So we have, for the initial single hardness coating that we've done, we have not, and that stayed the same, the friction stayed the same. We've not done that for the variable hardness coating. I would anticipate it staying the same, because the base of that is the same as the coating we did previously. It's just that we've tuned it as we've got towards the end of the coating process to become softer. So I would expect it to be the same, but no, we have not yet done either the durability testing or long-term testing.
Okay, thank you. So I have a question from here. A question here from Michael, who asks, after your endurance testing of these coatings in real-world conditions, when do you think they may be available for purchase?
That depends if somebody comes along and licenses them from us. So we're here. If you want to come and ask, then come and ask. Or I guess keep
we definitely want to do that, right? We definitely have the intentions of doing that.
That's the long-term
just a matter of getting all the science out. Yeah, exactly.
Okay, so there we go. Just waiting then. All right, so question here from Alan, who asks, does the coating require a honing process change?
Nope.
So we did not hone them any different than we would for the CRN type coating, or even say a plasma moly type coating. So the honing has been the same. I think we will be able to modify the hone because of this. That's something we are going to test in the next couple of months, is trying a different type of hone, because with it breaking in so simply and easily, we maybe be able to use a smoother surface that could reduce overall wear in the engine. So I think there is scope for that. We just haven't tested it yet.
Okay. All right. Very interesting. Thanks, Blake. So another question from Hamid here. How applicable is the coating to piston seal ring grooves and complex geometry with respect to line of sight?
Yeah, you do have to have line of sight. Some of the complex geometries might be a challenge with this particular process.
Yeah, it's just one of those things to consider with any physical vapor deposition process. It's line of sight. The plasma helps to a degree, but that's, if you want non-line of sight, that's, you want to look at a different type of coating methodology. But then that changes the dynamics of everything. Okay, we're moving on to now a question from Scott, who says, with the almost immediate break-in for production vehicles, do you think conventional oil could be used for manufacturing hot test and then be changed to full synthetic oil for shipment, since break-in has already occurred?
Yes, that would be entirely possible.
Okay, interesting. A question here from David. What were the surface finish parameters on the cast liner wall prior to testing and also after testing? It'd be interesting to understand any changes that were observed.
Did you take any of those measurements, like in the engine?
From the engine, yes, I do have them. So in micro inches, not microns, the surface finish prior to testing was in the 10 to 12 RPK range, with an RK value in the 35 to 40 range, with an RVK in the 50 to 60 range. And that was pre-run-in. Now with both coatings, we saw the RPK numbers drop, and they dropped down to the 5 to 7 range with both coatings, and then the RK would drop typically to 25 to 30. But the RVK really didn't change that much. It may have been 45 to 50. Some of them were as high as 55. So with the variable hardness coating, it was a little bit less, but not like a dramatic number less between the two.
All right, thank you. A very similar question in that vein from Chris, who asks, do you have a sense for how the results would vary at different RPK values?
Well, what I believe we can do is be able to take the RPK down much lower. In fact, when the engine goes back together for the next test, we're actually going to begin with an RPK of 5 to 7. So we're going to basically target that already run in surface roughness, and then begin from that to see is the coating able to still have that immediate break in even without the initial roughness.
Okay, interesting. Thank you. And a question here from Sean, who asks, do you feel there will be different results in the motor under varying thermodynamic conditions?
That's an interesting question.
Mm.
I don't think that anything. I don't think that it would be due to the coating. I think it would just be down to the normal variations that you see due to temperature of the lubricant and the general metal of the engine itself. And I don't anticipate seeing anything due to the coating.
I don't either.
Okay, thank you. Another question just in from Esteban, who asks, what is the maximum temperature that the coating can withstand without changing its properties?
I have no clue. We have not tested that.
Ah.
Well within a vehicle, but beyond that, I don't know.
Yeah.
It would also be interesting to see, not just the maximum, but the minimum as well. So that I would, if we were going to look at that, I would do pin on disc, and because we have the capability to do from liquid nitrogen all the way up to 1000 C, so we can test that out.
Oh wow. Yeah, that would be fascinating to see those results actually. And,
you've made me decide that's what we need to do next now.
What a great question. It would also be great to, I guess, quite interesting as well with the variable hardness as well. Maybe to, perhaps a little different from this type of testing, but to also look at, depth sensitive nano hardness, and then also varying temperatures of nano hardness.
Yeah, it would be.
Well,
yeah.
Well, what we're gonna do, because I already have them, we haven't honed them yet, is we're gonna try it with tuneable, a plasma spray bore. So we want to try this with like Nicosil, Alusil, these various bore coatings to see how it performs beyond just a regular cast iron or a gray iron type bore.
Yeah. And leading from that, I see a lot of uses for this, even in, say, electric vehicle gearboxes. And, getting good running on the gears there.
Yeah.
Absolutely.
Could have an effect on MVH and all sorts of different things.
Yeah, absolutely. I was going to ask as well, what other applications could you see for this coating? But there's already one, electric vehicles. So, okay.
I think for gearbox, yeah, I agree with Peter. Putting this on gear sets in gearboxes could be a real game changer.
Yeah.
All right. Fantastic. Another question in from Robert, who asks, can sample coatings be provided on custom seals other than rings?
Yes, we can certainly do that. It's a small batch process, so we can certainly set it up and put it on, and either test that in the labs here or send those parts back to you. Not a problem at all.
Okay, great. So, Robert, I mean, if that is of interest, I can send contact information after the event, and help get you two in touch if that's of interest. Let me know in the chat. Okay. Does anyone else have any questions? So we're about 5 minutes away from our sort of at maximum 60 minutes for today. So if anyone else has any other, okay. Not a problem, Robert. I will be sure to pass on your information. Okay. But yes, sorry. As I was saying, we're about 5 minutes away from our maximum of 1 hour today. So if anyone else has any questions, please do type them in the chat now. Okay, so we'll just give people a few seconds to type. Okay.
The reduction in friction was actually, especially when it followed the peak torque curve, to me, that was the most interesting part, that it really we saw that correlation between the bench test
Mhm.
and what the lower coefficient of friction was, and then you put it in the actual engine, and you see the friction reduction follow the exact change
Yes.
in load, right? So as cylinder pressure increases, torque goes up, and you
Mhm.
see the gain becomes larger as it increases, and then as cylinder pressure begins to decrease, it comes back down. That I love that. See that great correlation between what the bench test is telling us and then what the engine's telling us. It's the second time in the testing we've been doing with Peter and his crew at Southwest Research where we've been able to take what they've done on the bench and then put it in the engine and see a direct correlation between the two. As an engine guy doing the engine testing and product development, that is as good as you get. That's super exciting to be able to have a lot of confidence on that. Hey, when you do something on the bench, we're going to be able to back it up and verify it on the engine, and we're not going to get something completely different.
Okay. Thanks, Blake. So I think we have one final question from Alan here, somewhat similar to our to a previous answer, who just said, when can we expect to see this available? But an additional question of what do you think the timeline is? So I think if we focus on that for our final question for today.
I would say that it's not going to be this year. There's a fair amount of product development left to do. Blake can chip in as well because he's going to be doing some of that. And I don't know the time frame for some of what he's doing, but as you say, from a piston ring perspective, sooner. From other perspectives, we need to do some prove out work that we haven't even started yet. And as an earlier question said, we need to know what's the lower and upper temperatures that this can operate in before we can really start to look at applications.
Yeah, we have some opportunities in the next 3 or 4 months to do a lot of development work with this. We have a project that this is like a perfect fit for. So we're going to be able to work it in, and that will be the great part is we'll be able to compare it to the other things we've already compared it to and be able to see, and we have, if it plays out the way we hope it does, this is something that could go into some production parts sooner rather than later. But like Peter said, it won't be yet this year. And then based on how that goes, then hopefully it can spread and go much further than that. I personally think this is just an absolute, as you called it in the title, it's a paradigm shift. This changes everything.
Yeah, let's okay. We'll certainly be keeping our eyes on it to see how it goes. Okay, and I think with time, let's take just one. Well, I said final question. One final one from George here. Asked about any resistance to corrosion, especially with methanol.
I would anticipate that it would be corrosion resistant, but again, we could look at that pretty quickly.
Okay. So thank you both very much for your time today. Thanks for answering all of those questions. Thank you, the audience, as well, for all those great questions too. Thank you, Peter, for the fantastic talk today. It's very engaging, lots to think about. And thank you, Total Seal Piston Rings, for supporting this webinar. Thanks, Blake, for being here to answer questions as well. Okay, and with that, we're drawing the webinar to a close. So just a reminder as well, please do visit surfaceventures.org. You can find the recordings of all of our previous webinars there, as well as our workshops. You can sign up to our mailing list there, where you will receive our regular fortnightly newsletter. As said on screen, our next keynote will be on the 28th of September. We'll be taking a break for August, so please stay tuned to our website, emails, and our LinkedIn page as well for further updates. As mentioned before, please do sign up to our mailing list. You will receive our fortnightly newsletter when it is available, with the next available on the 4th of August. And finally, I'd like to say thank you all for attending, but also please do take your time to advertise these lectures and all that Surface Ventures does to your contacts. We hope it's interesting for them, and we'd like to continue to join our community. So for now, I'd like to say thank you, and I hope you all have a great rest of your day.
Thank you.
Thank you.
All right. Okay. Thanks all. Goodbye.